Let's get started on section 9.2, applications of parametric equations. So we are going to take what we have learned in our basic foundation of parametric equations in 9-1, and we are just going to apply that as it is demonstrated in real life scenarios. So let's look at problem number 1. So in these two problems on this first page, you'll notice at the top here it says that time is going to be measured in seconds and that distance is going to be measured in feet. So keep that in mind. So here we have a model rocket and it shoots off at an erratic angle. Its two directions of motion have the following equations. X equals 0.4 times t. Y equals -3t squared plus 18t. So you're going to see that here you can notice here for the x, they're giving us this in linear form. It's a linear equation. And the second one, they're giving us the y motion in parabolic form, which is what we call quadratic equation. So these are our two these are our two our parametric equations, and we're going to answer the following questions having to decide which equation we're going to use. So the first thing you're going to look at is the y value. Why? Because in this first question, they're asking us how high is the rocket after 2 seconds. Whenever we're talking about height, we're talking about vertical distance, okay? Vertical distance, we measure that in y. All right, so let us apply the y value equation. So y when t is 2, so y of 2 would be rewritten with t value being substituted with a 2 every single time. We apply order of operations that tells us that we will raise 2 to the second power first. And then we will do our multiplication and combine our like terms. So after 2 seconds, the rocket would be 24 feet high. So why not pause the video now, and I want you to do part B. Notice again, they're asking us to establish how high now is the rocket after 5 seconds. Now that you've paused the video, let us see if this is what you ended up doing. So similarly like the above equation, we're going to substitute 5 for every t value. And when you applied your rules of order of operations, your answer to this one would have been 15 feet. So it looks like at this point in time, the rocket is starting to make its way back towards the ground. So let's proceed to the next question, part C. When does the rocket hit the ground? So in this particular question now, no longer they're asking us for a vertical distance. They're asking us when. So when implies that we need to go look for time. So we're going to find time. Now, they're giving us a specific time to look for, and that is when does it hit the ground? Well, that gives us a hint, and it clues us in to the fact that our height off the ground is going to be set at 0. So what are we going to do? We are going to use the same equation again, but this time we're going to solve for t while letting our y value be 0. So let me scroll back up here. We are going to look at this equation, okay? But this time, this y value that I'm highlighting right here is going to be replaced with the 0 value because it hits the ground. So let's see if I can just scroll just enough where you can see the equation and be able to see the substitution. So that highlighted y is going to become a 0 equals -3t squared. plus 18t. Okay, sorry about the barking dog. So here we have 0 equals negative 3t squared plus 18t. So we need to solve for t. So in order to solve for t in this particular equation, we need to notice that this equation is actually a quadratic equation, okay, as established earlier today. To solve for quadratic equations, we use factoring to be able to solve for our specific values, in this case, our t. Whenever you go to factor any equation, the first factoring method you should always try is the greatest common factor method. And the greatest common factor method is the method where we look to see if any of the terms have some sort of common factor, the highest factor, that can be undistributed or factored out. In this case, let's look at the negative 3 and the 18. Both those numbers are divisible by 3. So that's one of the factors. So I'm going to write 0 equals, I'm going to pull out a 3. As a matter of fact, I'm going to pull out a negative 3. And then I'm going to look at the t squared and the t, and both of them share how many t's? 1 t value. So the greatest common factor in this case is a negative 3t. I'm going to open parentheses. Now, when I pull out a negative 3t, negative 3t times what will give me a negative 3t squared? Well, that would just be a t. Negative 3t times what would give me 18t positive? That would be a minus 6. Now, if you're confused as to what I mean by that, what I'm doing is I'm visualizing what times what would give me the previous answer. So negative 3t times t gives me negative 3t squared. Negative 3t times negative 6 gives me a positive 18. So I know that my factoring is correct because factoring is just reverse distribution. Once I finish reverse distributing there, or factoring, what I'm going to do is I'm going to apply what's called the zero product property. And what that means is that I'm going to take each one of those factors and set it equal to 0. So I'm going to take this first factor right here and set it equal to 0. And I'm going to take this factor right here and set it equal to 0. When I do that and solve for t, I'm running out of space here. So the first equation, negative 3t equals 0. If I divide both sides by negative 3, because I'm trying to get t by itself, then t would equal 0. So there's one answer. Okay. Then over here at t minus 6, I need to add 6 on both sides to solve for t. So then t will end up being 6 seconds. So I have two answers. So which one do you think is the t value I need to give the answer? Well, we know that our rocket is going to have some sort of parabolic effect. So what do I mean by that? So let's have a little visual here. So here you have this person and they're shooting off a rocket. Okay, so they're standing on some ground and they shoot off this rocket. Well, this rocket's going to make its way up into the sky and eventually it's going to land somewhere. Okay, well, the rocket started off at t equals 0 seconds. It launched and then eventually it's going to land on the ground. Okay, this is what we're looking for. And it landed 6 seconds later. So the answer that we are looking for is t equals 6 seconds. Okay, so let's proceed to part D. How far is the rocket when it hits the ground? Okay, so now they're asking us how far did it travel horizontally. So this distance right here is our question mark. And we're going to call that x distance because it's horizontal. So x equals what? What is the distance horizontally traveled by this rocket? So we were given, again, scrolling back up towards the beginning of the problem, we were given the equation for x, and this time it is x equals 0.4t. So we're going to use that since we're looking for distance. So x equals 0.4t. Now, in order to solve for x, we need a t value. Okay, well, we already established how many seconds it took to reach the ground, so x distance when t is 6 is going to be found by substituting 6 in for t. And in this case, 0.4 times 6 is going to give us a distance of 2.4 feet, which is, again, our answer for the horizontal distance traveled by this rocket. Now here's a question that's not being asked right now, but what if I asked you to tell me what is the max distance, not the max distance, the time at the max height of the rocket, which was this right here, okay? What I want you to notice is that the max value occurs halfway between t equals 0 and t equals 6 seconds. So if I was looking for that height, which is the y value, I would substitute this t value, which would be halfway between 0 and 6, which we know is 3 seconds. Correct? So notice that you can find the max height traveled, or you can also find the max distance traveled horizontally from beginning to the max. So keep those things in perspective, okay? So as far as problem number 2, I actually am going to have you practice this problem on your own. The answers are found in the answer key provided in our note-taking guide, but I want you to try problem number 2 on your own. Let us move on. Problem number 3. Now here we have two planes flying in opposite paths. Well, not opposite paths. They're following two separate paths. The question, and I apologize for it being such a morbid question, but will these planes crash? That's the question of the day here. Are planes 1 and 2 going to intersect, so to speak, if we want to apply this mathematically thinking? So they kind of give us a hint here on how to proceed with this question. Will they be in the same place? So I'm going to highlight same place at the same time. Will they be at the same place at the same time? So how does that help us? Well, what we're going to do is notice that we have plane 1 here being given to us. Parametric equations, not a F, it's a P. Let's try that again. We have plane number 1 here with parametric equations x and y, and then we have plane number 2 over here. Okay. Now, both have variables x, y, and t, both scenarios. We have to make an assumption, okay, in order to proceed with this problem. In order for them to intersect or crash, they have to occur at the same time and at the same place. So we are going to assume impact, okay? And what I mean by that is we're going to assume that these planes crash, okay? If they do impact, we are going to assume that the time is the same. Since the time is going to be the same, what we're going to do, or should I say the time is the same? No, sorry. Since we're assuming impact, the location of impact tells us, not the time. Oh my goodness. Let me erase this here. Let me rephrase myself. If we assume impact, we're going to assume that the location is the same. Okay? So assuming impact, that means the x have to be of the plane 1 has to equal the x of the plane 2. So x of plane 1 is 3t plus 1. And x of plane 2 would be 6t minus 11. Okay, impact means they're located in the same x location. We're going to solve for t here. If I solve for t, there's many ways. You could subtract 1 on both sides, add 11 on both sides, subtract 60 on both sides. It doesn't matter, okay? But I'm going to solve for t. And I'm going to, by doing subtract 1 first. So 3t equals 6t minus 12. And then I'm going to move the t over. So I'm going to subtract 6t on both sides. So 3 minus 6 is negative 3t equals negative 12. And now I need to divide both sides by negative 3. So my t value is going to end up being 4. So if they indeed crossed each other, they impacted, they crashed, so their x has to be the same. And if their x's are the same, the time of impact was 4 seconds for both planes. So far we have established as x is the same, the t value is the same. So now we need to check to see if y values are the same. Okay. If they are, sadly, the planes did crash. If they are not, that means, therefore, they did not crash because all the x's, the y's, and the t's have to be identical for the scenario. So let's check. Well, we know t is equal to 4. So let's calculate the y value location of plane 1 by substituting t equals 4. Okay, and if I can get this to erase, it's not cooperating with me. Stand by. Okay, let's do this. So y sub 1 of 4, was it? Yeah, 4 seconds. And so we substitute that. And so in this case, it will be 4 to the second power, which gives us a 16. Now y of plane 2 at 4 seconds, let us see. We substitute 4 for the t, so 2.5 times 4 plus 6. Well, 2.5 times 4 gives me a 10. Bring down the positive 6, and I end up with a 16. So sadly, we're going to notice here that the y values are the same. Therefore, the planes did end up crashing. Okay. Okay, so let's move on to the next problem. So here now we have a problem that looks like section 9.1. So we have x equals 3 plus 2 times cosine of t and y equals negative 1 plus 3 sine of t. Now, this looks exactly like the problems that you practice in 9-1. The only difference is that this time you have problems that involve trig equations, okay? Now, before we jump into this, I do need to rewind back to our first semester to kind of remind you a bit of the unit circle. So if you would, let us come over here and draw an x and y coordinate axis here. So I want to remind you guys of something. And I want you guys to recall that if we rotated this way around the unit circle, okay, what you guys would see is that we would end up here. We'd start here at 0 degrees, then would go up here to 90 degrees, 180, 270, and we'll make our way back to 360. Okay, do you recall that? Okay, so let me erase this down. Now, in this scenario, we're not going to use 0, 90, 180, 270, and 360. We're going to use the radians, okay? So here at 0, we're going to have a point that I need you guys to recall. At 90 degrees, which we call pi over 2, we had another value over here at 3 pi over 2. Sorry, not 3 pi over 2, pi. Then over here at 3 pi over 2, which is 270. And then we made our way back to 2 pi radians, okay? What were those coordinates? Well, the first coordinate here was 1, 0. Here was 0, 1, negative 1, 0, and 0, negative 1. Okay? So remember, you guys would have a big circle drawn through those points, okay? Let me see if I can do the best circle that I can, but maybe this thing will help me, this program. Yep, it's not really doing it. Can I stretch? Oh, look at that. I can probably stretch. Okay, so maybe you kind of get the idea of what I'm talking about here. Okay, so the other thing I need you to remember is the cosine value at an angle always meant you were looking for the x. And the sine of any angle always meant you were looking for the y. So keep those in mind. So that's your little review from last semester. Why do you need to know that? Here's why. So notice here they're wanting us to make a table of values and eventually sketch the curve. But let us just focus on making a table of values. In order to do that, we need to substitute the values in our table into our equations and evaluate. So x, when t is 0, means that we are going to rewrite that problem as 3 plus 2 times the cosine, cosine of 0. Well, the cosine of 0 means that we need to go to the unit circle at 0 degrees and look at the cosine value. Remember, cosine means that you're looking at the x value. So right over here, I'm going to look at when cosine is 0 and my x value is a 1. So I'm going to substitute cosine 0 with a 1. So 3 plus 2 times 1 is going to be 5. 2 times 1 is 2. 2 plus 3 is a 5. So I come over here on my table and I put a 5. Let's do this again. X at pi over 2. Let's substitute. 3 plus 2 cosine of pi over 2. Okay, if you want to put parentheses or not, it doesn't matter. Equals. So again, I'm going to go find out what cosine pi over 2 means. Well, cosine pi over 2 means that I'm going to look at the x value at pi over 2. So the x value at pi over 2 is 0. So let's substitute. 3 plus 2 times the cosine value at pi over 2 was a 0. So 2 times 0 is 0. 0 plus 3 is a 3. We keep going again. X of pi means 3 plus 2 times the cosine of pi. So we are going to find cosine of pi. Cosine of pi is what x value? Negative 1. So let's substitute. 3 plus 2 times negative 1. 2 times negative 1 is negative 2. Negative 2 plus 3 is a 1. So I'm going to keep doing this here. You can follow along because I'm going to have you do the next equation on your own. So notice all I'm doing is substituting the new value every single time. The key is you having to remember from first semester that cosine means find the x value, okay? So the x value again at 3 pi over 2 over here is 0. And so you're going to see, oh, that's not even a 0, but you know what I mean. What is that going to be? 3. And one more again. X of 2 pi. So 3 plus 2 cosine. And so we end up right where we started. And the cosine of 2 pi just means the x value again. So notice that we revert to the beginning. Okay? So there's that. Now, what I need you to do is I'm going to change color here actually. Let's change it to a purple. And let's have you do the y equation. Okay? So y equals -1 plus 3. Oh, I forgot to tell you what y value, y at 0. So now we're going to rewrite the y equation, but this time we're going to replace the t values with all the same angles that we just finished doing, but we are evaluating using the trig function sine. Okay? Now, again, remember I just told you here earlier, I'm circling it over here, sine is y. Okay, so this time when you're rotating around the unit circle, you are going to look at the y coordinate. So here we are going to, let me change the highlighting color here. Let's change it to green. We're looking at sine 0. Sine 0 is going to be the 0 degrees, the y value at 0 degrees. In this case, it's 0. So -1 plus 3 times 0 is still going to give me a -1. So why not just stop here or pause the video and you do the remaining substitutions for y and see what answers you get as compared to what I get. Okay, so go ahead and do that right now. Okay, so here are the answers all worked out. Okay, so go ahead and pause the video if you need to again so that you can compare what you wrote and what's shown in the table. So notice as I rotated around the table, all I did, I'm going to highlight it in green, is substitute the y value. Okay, those are the y values. So that's what I'm substituting every single time because I'm evaluating this. Remember, sine means y value. So I looked to the unit circle and I found the y value at 0, the y value at pi over 2, the y value at pi, all the way till I got to the y value at 2 pi. All right? And then obviously I just did the arithmetic and I got the answers that you see in the table. So what are we going to do? We're going to take those answers we have in the table and we're going to plot these points. So 5, -1 will go right here. And it's not writing for some reason. Let's try that again. 5, -1. And then what's the -1? 3, 2. 1, -1. And 3, -4. And 5, -1 tells us to go all the way back again. Okay? So if I were to connect these dots, okay, because I am now proceeding to sketch the curve, by the way, in the instructions. If I were to connect these dots, let's see here. Let's see if this technology will cooperate again. Okay. I want you guys to notice it's actually going to be more of a ellipse shape. So let's see if I can perfect this a little bit more. And stretch it. There we go. So notice it's going to have the shape of an ellipse. Okay, and we just studied that in Unit 8. So we have an ellipse being drawn right here. And here's my challenge to ask you. If you look at this ellipse right here, what would the center be? Well, we can see and visualize that the center of the ellipse is right here at coordinates 3, -1. So I'm going to write down this information here. So the center would occur at 3, -1. if I were to ask you what was the A distance and the B distance, okay, well, remember with an ellipse, the A distance was the long distance from the center to the vertex, which if you count, this distance right here would be your A distance, and that was a 3. Your B distance was the distance from the center to the covertex, and that distance there is a 2. So I'm going to put this as a 2. Okay, so hopefully you guys are visualizing that well enough to see that information. And you'll see why I'm asking you to look at that, okay? Here's the connection that I want you guys to make, all right? Now, before I proceed to showing you guys how to eliminate the parameter, let us finish sketching this curve because we still need to include the direction of the graph. So remember, when you guys are doing sketches of parametric equations, you must always provide, whoops, I don't know what I just did, but we can ignore that. We can always provide arrows, okay? So you will draw arrows as to the direction that you plotted in. And every single time, you should also always provide me with t-values for every single time you plotted. We started with a t-value of 0. And then we went to the t-value of pi over 2. Then we plotted t-value at pi, t-value at 3 pi over 2, and made our way back to 2 pi. So don't forget to label each point every single time, okay? Now, as far as getting ready to show you how to eliminate the parameter is our t-value. What we're going to do here, let's see if I can, I don't know if I can erase this all in one shot. Let's see if I'm able to. Am I able to do this? Delete. There we go. So here I needed the space, so you guys might need a little extra paper to attach for problem number 4. But here's what we're going to do, okay? Looking back again at first semester, so looking back, you're going to recall that we had something called the Pythagorean identity, or identities, okay? And one of the most important, and as a matter of fact, it was the first one you learned, was that cosine squared t, or theta is the way you guys learned it last semester, plus sine squared t was always equal to 1, okay? So keep this in mind. This was one of those formulas that you guys had to learn last semester, okay? So what I'm going to have you guys do is we are going to replace those values with the equations that we have, okay? But we need cosine and we need sine. So here's what I want you to notice. For x, we are going to need to solve for cosine. So in our first equation, we had x equals 3 plus 2 cosine of t. To solve for cosine, I am going to need to get rid of the 3 and the 2. So let's subtract 3 on both sides first. So that would leave me with x minus 3 equals 2 times the cosine of t. Now I need to divide both sides by 2. And once I do that, now my cosine t is all isolated. Okay? I'm going to do the same thing with the other equation. Y equals negative 1 plus 3 sine of t. I'm going to add 1 on both sides. So y plus 1 equals 3 sine of t. I'm now going to divide by 3 on both sides so that those 3's can cancel. And now I have y plus 1 over 3 equals sine of t. Now that I know what cosine and sine is, I am going to substitute it back into the equation of my Pythagorean identity. Notice that I had wanted, let me get another color here. I had wanted cosine squared t, okay? But here they're giving me cosine t. I need it to be squared. So what I'm going to do is I'm going to take this and I'm going to raise this to a power of 2 and raise this to a power of 2. So I'm going to end up with x minus 3 over 4. And this x minus 3, I'm going to raise it to the second power, is cosine squared t. Okay? So I raise the power of 2 to every single thing. I'm going to do the same thing over here. I needed sine squared. Okay? So I am going to take this sine and I'm going to square it, and I have to square the other side as well. So I'm going to square this, I'm going to square this, I'm going to square this. So I end up with y plus 1 all squared over 9 equals sine squared t. So if that's true, and my statement is that cosine squared plus sine squared has to equal 1, well, I already have cosine squared. It's x minus 3 over 4. And let's put the little 2 there. I need a sine squared. Well, here is my sine squared. So I'm going to substitute it into my Pythagorean identity, plus y plus 1 squared over 9. And then I'm going to put my equals 1. And so here now is my rectangular equation. I remove the parameter of t, and I'm done. So what do I want you guys to notice? I want you to notice here the following. This is the equation of an ellipse. Notice that the center is going to be, you told me the center was supposed to be 3, negative 1. Well, if you take the opposite of this number, it's going to be a 3. If you take the opposite of this number, it's going to be negative 1. You told me that a equals 3 and b equals 2. Well, the square root of 4 is 2. The square root of 9 is 3. So we know that because the 9 is the bigger number and it's underneath the y, it's going to be a vertical ellipse, just like we said over here on the left and as shown in our picture. So our rectangular equation is definitely matching what our parametric equations sketched out to be. Okay? So the intent of this problem is to help practice again your 9-1 skills of sketching. It incorporates prior knowledge of semester 1 with trig. And you are literally solving for cosine and sine in order to solve this Pythagorean identity. So you will always solve for cosine and sine and square it and put it into this equation to set it equal to 1 to come up with your rectangular equation. Okay? Now in the next couple of problems, it's not as much work as the one you just finished doing. Notice that I am giving you an equation here, okay? I'm giving you that Pythagorean identity all over again. Cosine squared plus sine squared equals 1. And this time I'm giving you the actual rectangular equation. In this case, I'm giving you specifically the equation of an ellipse. So whenever I give you the equation of an ellipse, I want you to please make sure that you use this equation here, this Pythagorean identity. Now, what you're going to notice is that I'm going to have you pair up your equation, your Pythagorean identity equation with your rectangular equation. So, cosine squared is going to pair up here with this first term. We've got the plus here, just like we have the plus here. And this sine squared is going to pair up with this second term. And this one here is pairing up with this one here. So we're good. So let's match up our terms. So we have an x plus 5 squared over 9. And that's going to equal the cosine squared t of the other equation. I'm going to put a divider here. And then I'm going to put y minus 2 squared over 16. And I'm going to set it equal to the other equation term, sine squared t. And what I want you to do here is I need you guys to solve for x here. And I want you to solve for y. Now here's what I want you guys to realize. In previous problem number 4, we started off here at x equals 3 plus 2 cosine t and y equals negative 1 plus 3 sine t. And we went from this highlighted yellow to down here. I know that's a lot of arrows I'm drawing, right? Now I'm asking you to go backwards to what you did in number 4. We're going backwards. So here's what I mean by that. So the first thing you're going to do is you're going to square root both sides. So if I square root, so in essence, I'm asking you to pretty much do this. I'm square rooting both sides. So when I square root x plus 5 to the second power, it's just going to end up being x plus 5. When I square root 9, it's going to be a 3. When I square root the cosine squared of t, well, it's just going to be a plain cosine of t. Okay? I'm solving for x, so I'm trying to get x by itself. So that means this 3 has to move to the other side. The 3 is dividing, so it needs to go to the other side, multiplying. So 3 times cosine t will just be 3 cosine t, or 3 times cosine t, written like that. Now I need to move the 5, so I need to subtract 5 on both sides. Whoa. And so when I solve for x, it's not letting me write, you'll end up with 3 cosine of t minus 5. So there is my first equation, my bad. We're going to do the same process over here. Nothing's changing. I'm going to square root and square root. This time I am solving for y. So we square root. The square root of y minus 2 squared is just going to be y minus 2. The square disappears. The square root of 16 is a 4. The square root of sine squared, the square disappears, becomes just a sine of t. Again, move the 4 to the other side, multiply it. So y minus 2 equals 4 times the sine of t. And then I need to add 2 on both sides to isolate the y. So I end up with y equals 4 sine of t plus a 2. And now you went from a rectangular equation to two parametric equations because you reintroduced the parameter t. We've got one more problem to do. Notice in problem number 6, this time you are being introduced to a hyperbola. Okay, remember hyperbolas have that subtraction sign there. Okay, so I want you guys to notice that a new equation is being used. You're not going to use cosine squared equals sine squared. Your cosine squared plus sine squared equals 1. You're going to use secant squared t minus tan squared t equals 1. Okay, this as well is another Pythagorean identity, just in case you forgot again from last semester. Okay, you will use these with hyperbolas, but the process is the same. You will pair up secant squared with the first one. You'll pair up tan squared with the second one and set them equal to each other. So secant squared t equals y minus 1 squared over 25. And the other one is tan squared t equals x plus 3 squared over 4. Just in case you're wondering, I purposely rewrote them flip-flopped from the previous one just to prove to you that it doesn't matter. Okay, it doesn't matter which one you write first. Okay, so I flipped these around, but the process is still going to be the same. You are still going to square root both sides first. So this becomes secant of t equals y minus 1 over 5. This one's going to become tangent of t equals x plus 3, the square root of 4 is 2. You will still get rid of the denominators first by multiplying them on the other side. So 5 times the secant of t equals y minus 1. 2 times the tangent of t equals x plus 3. And the last step will always be either add or subtract on both sides. So for the y, you're going to add 1 on both sides to solve for y. I'm done with that first equation. For this equation on the right, you're going to subtract 3 on both sides. And you're done. So there's your second parametric equation. So hopefully you understand this. I am going to actually leave problem 7, and this should have been problem 8 for both of them to be tried by you. Please notice that this one's the ellipse one and this one's the hyperbola one. Okay, so make sure you are using the correct Pythagorean identity when rewriting this rectangular equation into parametric form. The final answers to these are also in your notes. Thanks again for watching.